Thank you. Good afternoon. So in these few minutes I will talk about the application of the new star satellite to the study of the RTVBLX, that means extreme blazars. And in particular we will see what an extreme blazar is, why they are so important, but above all, how they try to find them, because it's not, there is no automatic procedure to find them. In this article they will use a multi-wavelength approach for this study. Maybe you remember that a blazar is an active galactic nucleus with a jetted active galactic nucleus with the jet pointing directly toward us. And in particular, these are called blazars. Blazars have a very particular SED characterized by two main peaks. The first one is called synchrotron peak, the second one inverse Compton peak. We think that a sea of hot electrons in the regions close to the black hole are accelerated into the jet, and they lose energy through via synchrotron radiation, and they produce the first peak. Then the radiation is kicked at the highest energies via inverse Compton process, and the second peak is produced. In particular, we'll see how they, in this paper, they try to find new extreme laser candidates studying the X-ray band and the high energy, very high energy band. Maybe you remember that a phenomenological sequence exists in this category of blazars, and in particular the extreme blazars are the most extreme blazars in which the two peaks are shifted to the highest energies, and in particular the luminosity is the lowest one with respect to the category. So this is a phenomenological sequence, and we will see that in the X-ray band, the extreme blazars should be the only ones that have the first peak, the synchrotron peak, in this band. So, in particular, we find that the synchrotron peak in the extreme blazars are characterized by a frequency at more than 10 to the 17 Hz, and the second peak should be above 10 to the 25, 26 Hz. In particular, they have a very hard spectrum, both in hard X-rays, both in gamma rays. The low luminosity and the two peaks that are shifted to the highest energy should reveal the galaxy for the objects that are not too far from us. So a main question should be that what's the difference between high synchrotron BLAC and extremely high synchrotron BLAC? It's not an only matter of a sort of division between these two numbers of frequency of the two peaks. The difference is due to the fact that the main model that we use to study these objects, the main model that is called synchrotron self-Compton model, works very well in HBL, in the standard high synchrotron peak blazar, but it doesn't work so well in extreme blazars. The reason is that extreme blazars are so energetic that, in particular in the very high energy band, they should be affected by Klein-Shina effect. So Klein-Shina effect that kills the cross-section in the highest regime. So other models should be preferable with respect to the standard synchrotron self-Compton model. And in this paper, they try to see if this works for EHBL, in particular for a sample of well-known EHBLs, extreme blazars. I would like to show you a very simple example on why it's so difficult to find extreme blazars. In particular, here you can see a source in which this is the multi-wavelength source, the multi-wavelength SED. In particular, you can see that only few data are available in for the source, radio data, optical data, and just 1, 2, 3 points of in the X-ray band. So you understand that yes, this is maybe that in green is that one in green is the galaxy, but the problem is that when I try to fit this data in this LCD with a sort of the shape of the synchrotron peak, yes, this could be an extreme laser, but also not extreme shape can work. So you see that it's very easy to have both solutions available for this source. And this is a problem. But in this paper, they try to understand if this source is an extreme laser or not using the NuSTAR satellite. You can see the sensitivity of a NuSTAR satellite, and this is very, very good for EHBL extreme laser hunting, because you can understand, you can measure the peak, where is the synchrotron peak of this source in the hard X-ray band, and this is the only instrument that is available for this kind of studies. So they try to use NuSTAR satellite, NuSTAR observation, but also UV observation, Swift observation, high energy observation with Fermi-LAT for 6 sources, and they try to characterize the synchrotron peak of these sources. In particular, they produce 2 tables that are very interesting. The first one, in the first one you have the 6 sources, and they find that 5 out of 6 sources are indeed extreme lasers, but one of these sources is not an extreme laser, because the peak is the third one, because the peak is below 1 keV, that is the limit that we use to define extreme laser. And in fact, they see that in the Fermi-LAT analysis in the second table, the properties of this source are quite different from the other sources. In particular, the Fermi-LAT spectral index is very low with respect to the other ones. So we understand that they tried to fit these 6 sources with a standard synchrotron self-quantum model, and yes, they did it. It was successful, but the problem is that they need extreme parameters to fit these sources. In particular, here you can see, for example, the red box is the parameter called gamma break, that is related to the position of the synchrotron peak. And 10 to the 6 is a very high parameter, very strong parameters. In blue, you can see the magnetic field that is very low, of the order of the milligauss. In yellow, you can see the Doppler factor, that generally it's more or less between 10 and 30. Here, you can see that it's more or less 50, 60. And at the end, you can see also the ratio between the energy of the electrons and the energy of the magnetic field. And we would expect that a sort of equipartition should be present, but this is not the case. You can see that we are out of the equipartition of 3, 4, 5 orders of magnitudes. That is a very strange thing. So yes, the standard synchrotron self-quantum model works, but with very extreme parameters. So the conclusions of this paper are that they succeeded in finding the synchrotron peak for this sample of 6 well-known extreme lasers, and they find that the properties of the only source that is not an extreme laser, they are quite different. They are quite different from the whole sample. So, and they find that the standard synchrotron self-quantum model works, but not completely, let's say, with extreme parameters. And they succeeded also in selecting the models that can, the lepto and leptodronic models that can fit these extreme lasers. So they put some constraining, some constraints in this study. So I think that it's very important. That's all. Sorry.
Okay, thank you. There's a question?
Yes, first of all, when you talk about new star to a general audience who doesn't have much familiarity with high energy observations, I think it would be very, very good to explain that, first of all, explain that it is an imaging telescope. And so these are data that were not available before, and such instruments didn't exist before, and we can get rid of the background or background sources. The spectrum that we get is very clean. I have two corrections to the English: parameter, and not parameter doesn't exist, and source.
Source.
Yes, so these are words that you're going to use very often. So.
Thank you.
Okay.
Other questions? No? Okay.
Thank you.
Thank you, Luca. Okay, so now we have our second speaker, Virginia. She is going to present her slides via Skype, so just a moment that we make the connection. Ciao.
Ciao.
Ok, allora aspetta che ti metto.
La sentiamo e lei ci sente, mi sembra positivo.
Ok, let's go.
Okay, may I start?
Yes.
Okay, can you hear me well?
Sentite?
Okay, I can, okay, così meglio?
Aspetta.
E la mattina deve spostare l'audio sulle casse, non sul computer.
Dov'è?
È qui sopra.
Sei lì?
Sì,
Falla parlare Virginia.
Guardando qua.
Viene dalle casse del computer.
Ok, arrivo subito. Parla?
Ok, sentite?
Ok, un attimo. C'è per definito.
Pronto?
Un attimo. Aspetta.
Ok.
C'è già. No, non è il massimo. È già in HD. Uscita, quindi è Skype. Qualcosa. Prova adesso. Ah no, aspetta.
Sì, mi sentite?
Sì.
Ok, va bene, così mi sentite bene? Posso partire?
Vai, parti.
Okay, so today I'm presenting this paper from James and Percival about the relation between star formation, suppression, and the presence of a bar in galaxies. So next, please. So the aim of the work by James and Percival was to explore the effect of bars on disk star formation and to place constraints on the lifetimes of bar episodes. Their analysis is focused on regions swept out by the bars of suppressed star formation activities, which are called star formation deserts. They measured H-beta absorption strengths in 21 bar galaxies and compared them with theoretical stellar models in order to identify the time of the last significant star formation activity. So in the next minutes, I want to discuss about the relation between bars and star formation and present the results obtained so far in this field. And then I will introduce the sample obtained, analyzed in this work, and largely discuss the results of this analysis. And finally, I will address some open questions. So next, please. So bars are a common feature in these galaxies, and there is a large discussion which is focused on the possible role between bars and the secular evolution of galaxies. For example, it was suggested that bars could build bulge components at the expense of disk material, or bars could control the star formation, the overall star formation rate in a galaxy. In a recent work by Haywood et al. In 2016 related to the Milky Way, the author observed a star formation turned down a star formation turned down, possibly driven by the formation of the galactic bar. As you can see from the plot, the author traces the star formation history in the inner part of the Milky Way, which is plotted with a yellow line. And as you can see, there is a decrease at 8 gigayear in the star formation, even if the gas fraction, which is traced by the black line, is high. So there must be a process that can pause the star formation. This suggestion was also confirmed by other studies, which generally shows that bar galaxies have lower star formation rates than unbarred ones. So next, the same authors previously showed in another paper that bar galaxies have a radial pattern of star formation that is totally different from their unbarred counterparts. In particular, the barred galaxies showed an almost complete suppression of star formation in the region swept out by the bar, which they defined as the star formation desert. And this desert is accompanied with, in many cases, by an increase in star formation both in the center of the bar and in a ring just outside the ends of the bar. In this plot from James et al. Of 2009, you can see the H-alpha radial profile in galaxies divided into unbarred on the left side and weakly barred in the center and strong barred in the right part. The H-alpha profile is used to trace the young stars. So as you can see, the profiles are very different from the left to the right side of the plot. So the star formation desert is dominant in early type galaxies, while late type bars are mainly associated with the star formation along the bars themselves. So a first possible explanation of this star formation suppression is that bars can induce shocks and sharing gas motions sufficiently strong to stabilize the gas against collapse. Or in alternative, the formation of a bar can deplete gas in a large region. So next. So concerning the sample and the instrumental setup used by the author in this work, they analyzed 21 barred galaxies at distances between 10 to 80 kiloparsec with a wide range of Hubble types from SB to SCD, and with the bars classified as strong, weak, and intermediate, and also one double bar. In the picture, you can see some example of the analyzed galaxies. They performed a long-slit optical spectroscopy with the intermediate dispersion spectrograph mounted on the Isaac Newton telescope, and the slits were aligned perpendicular to the bar, and the setup was selected in order to maximize the sensibility in the region of the H-beta absorption. So next, please. Concerning data reduction, all the standard stages were performed. And finally, 2 spectra per each galaxy were extracted in desert regions, one per each side of the nucleus. The main parameter extracted from the spectra was the H-beta absorption line equivalent width, which is very sensible to the age. And to take into account for the age metallicity degeneracy, they also measured the metallicity sensible magnesium B feature. And they perform also emission line measurement to correct the emission line contamination of the H-beta absorption lines. So in the table are presented the results obtained for part of the sample. So next. So in this plot you can see the main results of the paper. Each point corresponds to a measurement of the H-beta absorption equivalent width from an individual star formation desert region, plotted against the metallicity sensible magnesium B feature. The points are overlaid on a grid derived from a model where the star formation started 13 gigayears ago, proceeded at a constant rate until an abrupt and a complete cessation of star formation happens, where in the model the epoch of this cessation is the free parameter, and is allowed to vary from 4 gigayear to 50 megayear, as you can see from the almost horizontal line of the grid. The model is traced for different values of metallicity, from a very metal poor case to the metal rich one, and that is showed by the almost vertical lines. So the inferred truncation ages by this analysis, that are the time since the last strong episode of star formation occurs, cover a wide range in ages, from 4 gigayear to about 100 megayear. But this spread seems to be real because it's greater than the errors are associated to the measurements. So next. In this plot you can see the same results as before, but presented on a galaxy by galaxy basis. Pairs of regions from the same galaxies are joined with dashed lines, and the symbol in the center of the line represents the mean value of a given galaxy. This representation is useful to test if there are differences for spatially separated parts of a star formation desert region within each galaxy. In general, the dashed line seems to be short, so this can indicate that any such inhomogeneities in each galaxy must be small. So, in fact, the authors measured the median difference in equivalent width within each galaxy, and so that it was comparable with the median error on the measurements. Different morphological types of galaxies are distinguished by different point types, and it seems to be there are no striking trends, but the most of the main peak of galaxies around 1 gigayear seems to be, which are represented by the open circle, are SB galaxies. And there is also a slight excess of late type galaxies with young bar ages, which are the star points. But the main conclusion from this plot is that a broad range of truncation epochs is seen for all galaxy types. So next. As an alternative to the model of a complete truncation of star formation, the authors also explored a possibility that a downward step in star formation may occur. After this downward step, the star formation could continue with only 10% of its previous rate. In this case, the inferred step ages turned out to be fairly twice the truncation epochs. However, the authors underline the fact that many of the analyzed star formation desert regions show extreme star formation reduction, as indicated by the weakness of any detected emission lines, which brought them to exclude the possibility of downward step in star formation. There is also the possibility that young stars from elsewhere can be mixed in the star formation desert region. So this mechanism would have the effect to introduce a younger stellar population without requiring ongoing star formation. So next. So in this plot, the star formation points are overplotted on a model grid for an exponential decline star formation history, rather than a strong abrupt. Different models are traced for different exponential declining time, tau, and different metallicity. In this case, the star formation desert cluster around exponential decay time of about 6 gigayears. So this result again would imply to observe now about 10%, still a 10% of star formation, since the ages of the galaxies are just twice the exponential decline time. But since the authors already ruled out the possibility of a 10% of ongoing star formation, they could conclude that it is better to imply a truncation events rather than an exponential decline. So next, okay. The ages measured in this work by the author were compared with both theoretical prediction and other observational estimates of bar ages. Both these analyses say that bars tend to form in the early stages of a galaxy evolution, become stable and long-lived. The timescales for the stabilization seem to be longer for gas-rich galaxies, and this expectation seems to be in agreement with the trend found by the author, where the latest type of galaxies have the most recent established star formation desert regions. So next, okay. So finally, the authors try to sketch out a possible time sequence of events happening in a bar galaxy in terms of star formation activity. First of all, the most probable initial response to the formation of a bar is the enhancement of star formation activity. This should be a short phase in which there should be a radial transport of gas to nuclear regions, and this could trigger strong nuclear star formation and star formation along the bar. And this phase can be seen at the current epoch, observing the late type galaxies, as you can see in this picture, where you can see the star formation in all the galaxy. After this short phase, the bars strengthens and suppress star formation in a large radial range in the here discussed star formation desert region. This should be a long-lived phase with time scale of gigayears. The star formation can continue in the nucleus and in a ring outside the bar, but this is not sufficient to compensate the total suppression in the star formation desert region. However, the lack of ages greater than 4 gigayear imply that the star formation rate does not last indefinitely. So the authors asked themselves, what can happen after this phase? Can the galaxy restore the star formation? and undergo, for example, multiple barred phases, or does the star formation suppression propagate outwards? So in order to answer to this question, they will work in a future. So next, finally, a brief summary of the results. First of all, the author could confirm the star formation desert phenomenon. And in this work, the absorption line strengths can be fitted by stellar population with a constant star formation followed by an abrupt and complete cessation of star formation, where the epoch of this truncation is the free parameter of the problem. The inferred truncation epochs vary between galaxies from 0.1 to about 4 giga-year. And the truncation ages from independent regions within the semi-galaxies are consistent. There are indications of later truncation in star formation in late-type galaxies, which is consistent with theoretical models. And so there are still open questions. For example, which is the physical process related to this observed star formation desert phenomenon? Is the gas stabilized against collapse, or is completely depleted in the region of the bar? And another question could be is related to what happened after the star formation desert phase. Does the star formation suppression propagate or stop? So to answer to these questions, more work is needed, both theoretical and observational. So thank you for the attention. I hope you could follow me from distance, but thank you.
Okay, are there any questions? No? Okay, so thank you, Virginia. And that's all for today. See you next Monday.
Ciao.
Bye.
Bye bye.